Oh, and he always it's super bad. Really? Scams are always one. Oh, okay. I thought this time it was like 2 days after. Probably. I feel like everyone did way worse than expected. Oh yeah, last time it was the next day, wasn't it? Not the day of. Was it that night? Oh. Okay. I checked it that night. Okay. He always done that though. He did it last semester. It was really super.
Okay, we have to start the class for now. So before that, I want to hear your feedback again about the test. I need to put your grades on the grade book after some time. But it looks like it's much better than test one. I'm a little bit impressed. I think a couple of students got 100 out of 100, and there are more than many students have got about 90. It's a very big class. I don't know how many of you guys, but in percentage wise, you did pretty better than just one. Okay, but even then, I want to hear your feedback. So your feedback is very important. We will need to focus on the panel now. Anything you want to tell about the test 2? How you feel? It's okay? You feel comfortable? Or still it's too difficult? Or if you see something that you are not expecting, something like that, give me your feedback. If you like it, then I just keep on doing the same thing. What's your feedback?
Can you put more math on the test? More homework questions?
You want to put more math?
Yes.
Okay. So your colleague says okay, more math. What about other people? Do you want to tell anything about them? No comments? No suggestions? So are you okay with the test 2? You like it then? Okay. Alright, so
No, it's not, because the multiple choice is a quarter of a chance.
I had a conversation.
Yes, it's hard to start. Yeah, math is just a formula, but
and I will canning this or canning this, but it depends on what your reference. So how are you gonna go about that for that?
No other class
So,
is just gonna give you the formula.
I took one of the colleagues here.
Why don't you want to take it?
In my office.
I think it's
To me, we are talking like a very general physics over here. It's not like something special, like money for that, in general, I look into it and said, of course, in space of condition it might exist, but we're just talking a general starting where a single charge can exist. Like you have a one, it's like a particle, for example, electron, it has a single charge. Monopole means like a one pole for electrostatics. One pole means one charge. It can exist. Okay, but it's not like an official like some people are putting it. In special case, it might exist. So basically, we go with our general perspective. So in that case, electric monopole can exist. Okay, and then I saw one of the professors talking about I gotta give that and there's a more detailed information, but he's very positive that he's very strong on that argument that but magnet, no way that you can separate non-current out. Okay, there's no single. There's one difference between the electric monopole, the electric dipole, magnetic. Okay, so it's possible because a charged particle carry a particle. A particle can carry either positive charge or negative charge. There's one particle, for example, proton is a particle, is a fundamental particle. It can singly exist without being the presence of another particle like electron. Right? So that's the reason that it's possible to have like one. Okay? But there is no particle that has one north pole, that has one south pole. Have you seen any fundamental particle that has only north pole and that has only south pole? No way. It's a purely quantum phenomena. I don't know how many of you guys are interested. It's a quantum mechanics. Each particle has a magnetic moment because of the spin. Okay? I don't know how many of you guys know about spin. The electron has a spin that is 1/2. It's a fundamental intrinsic property of a fundamental particle. Okay? And that is the reason for having the magnetic moment. Okay? It's a consequence of having that, this, spin. And the spin contributes to magnetic moment, and from magnetic moment you will get a magnet. Okay? So because of that, it's not possible. Okay? So we can always, discuss about that. We can always discuss about that. If you want to have more information, definitely, you can stop by to my office. We can have a more discussion because no one in this world is perfect. We want to learn physics. We want to master, right? I mean, definitely. And if there is something I'm missing over here, definitely please, let me know. Any further comments? Yeah.
So the tests, do they exist or do they not exist?
Of course, for electric monopole, yes, exist.
They do exist?
Yeah, I mean, you have a single proton, you have a single electron, right? That's a one pole.
Oh, in the review?
No, we never do like that. We never do like that. Yeah, I mean, I explained about putting the magnet in pieces, right? Okay, so if you don't have any question, we're gonna focus more on final, because final is the one that's gonna be a little bit comprehensive. So I already gave all the credits for you guys, 20 points credit, I believe, 5 points you got on the test too. I gave a bonus question. It's supposed to be 100 points in total, I gave 105, okay? And you got like a homework credit, extra homework credit. You got test correction, you got attendance credit. I gave 20 points to you guys, and from now on, you will not get any credit for sure. Whatever score you make, that's your score. If you have any issue with your homework, okay, please fix the issue as soon as possible. We never go back, okay? We never go back. At the moment, later on, we say, hey, I just need 1 point to go to A, letter grade A, or if I get 1 point to go letter grade B, I really want to pass this class, but I need 1 single point. And you kind of go back to my homework number 1, and because I miss some units or something, so that I lose some point, I want to fix my grade. No way you cannot do it. Okay? So if you have any issue with your homework, talk to the grader as soon as possible and fix it. Okay? So if there's some grader has made a mistake, talk to the grader as soon as possible. Okay? I'm gonna give 1 week time to fix everything. Okay? And I'm gonna send even email about that. Okay? We never go back after that. Okay? So whatever grade you make, that's your grade. Okay? Because I gave everything to you. So I give 20 points, that's a lot for you, okay? Any other comments? No comments? Alright, if not, I need to focus on the syllabus and then a lecture content now on. And this is the one of the homework from I assigned you guys, and this was one of the problem I asked in the test also. I think you did pretty correct on this one. This was so easy problem. Now we're going to talk about the electric potential due to dipole. It has a lot of mathematics over here. So, but I want to give some of the information, and you take care of that. Okay. So I'm going to assign this one as a homework. So you are trying to find the potential due to a charge. If you have a charged particle, let's say single charge, okay, then you are talking about electric potential at a distance of r. Okay, the potential due to charge, let's say Q1 at a distance of r is given by D1 is given by K Q1 over R. Okay, R1. And if you have a multiple distribution of charge, let's say you have a more charge coming from like another, let's say you have another charge, let's say it's again positive charge, let's say Q2, and you are at a distance of, let's say R2 from this one. And if you want to find what is the net potential at point P, then you need to add them together. So you have potential from charge 2 is K Q2 divided by R2. So if you want to find net potential, D net, it is D1 plus D. You need to add them together. So if you have a charge, two charge, you add them together, D1 plus D2. But if you have a more charge, definitely you need to add all of the contribution. And that was one of the problems that we solved recently. If you have a charge distribution is square, and if you can calculate the distance between the distance at a point P, you can contribute version from Q1, Q2, and Q3 to Q4 at a point P, and you just add them together. And it's easy addition because potential is scalar quantity. Okay. If it was vector, that would be a different story because vector has a direction, but potential is scalar quantity. So you can add them together like a simple mathematical calculator. Okay. Okay. So now, if I want to find what is the potential at a point due to a dipole, then dipole. You have a two charge, okay? So you have a charge, negative charge and positive charge, and you have some separation of distance r. Okay, you can call it d also if you want. D. You have a d, okay? So it's a dipole because you have a positive charge and negative charge, and each charge is equal in magnitude. They are just opposite in the nature. So you can consider at any point, from the center of the dipole, let's say you have an R point, center of dipole, it's a point P, okay? Let's say R. But it's the center of the dipole, but this charge has a different distance compared to it's R plus, you have R minus. I couldn't make it better picture, guys. Let's take a look at the slide. This negative charge are different distance. Okay, R plus and R minus. Okay. Okay. This is the okay, you have R plus and R minus. R plus. So if you want to find what is the potential at point P, definitely the positive charge does have a contribution, right? And negative charge doesn't have a contribution. And net gonna be if the positive charge has a contribution of big loss, and if negative charge are contributed to B minus, then the net potential is gonna be the sum of the contribution from positive and negative charge, right? This is what we have done, over there also. The net potential gonna be sum. So, I give R plus and R minus over here. So, the potential due to this charge, plus charge is gonna be K cube, positive charge definitely, divided by R plus. And this is the K, it's a negative charge minus Q divided by R minus. Okay, the net potential will be like this. So if you want to simplify this one, definitely K is like a positive. You can just take, K is a constant, constant. Q divided by Q also is a common over here because it's a Q, it's a Q. So you're gonna be 1 over R plus, and the negative charge, negative, positive, negative, 1 over. The net potential at point P at a distance of R from the center of the dipole going to be like that. Now, the rest of the step going to be simple mathematics over here. So, to find the net potential, we do some mathematics over here. Because R plus and R minus, they are the so R plus and R minus, they are like a distance from the positive and negative charge. But I want to express the potential in terms of R, because R is the one that I know. This is a distance from the center of dipole to the point P. So my job is that to simplify and express R plus and R minus in terms of R. So how I can do it? So there's a couple of ways. Let's consider that. This is the like a G direction. G direction, and if it makes an angle of theta with this G direction over here, you can do simple geometric construction like that. Okay. The dipole, the charged particles are very close to each other. They are very close to each other. But this point is very far away from the, this dipole. So this distance, the D is very small compared to the R or R plus. Okay. So this is one of the approximation we have to do. So you can do your own way if you want, but I can simplify this one further. V net is like a K Q. Let me say 1 over R plus minus 1 over R minus over here. So you can simplify this one further. Let me do some K Q. If you take the least common factor R plus R minus, it will be R minus R plus. Okay. So you have V net KQ. Now, R plus and R minus, they are distance from the positive charge and negative charge. And if you consider that, like a very far away, the distance R plus and R minus is very comparable to R. It's an approximation, don't tell me that, hey, they are same, but they are very close. Okay? So, so over here, R plus R minus is very comparable to R. this might be a little bit different, but you know, very close to this one. So that this is R. This is R now, approximately R, and this is also R. So R, if you multiply them, it will be R squared. The denominator is going to be R squared. I express this one in terms of R. Now, you need to express this R minus and R plus in terms of R. How we do it? And it's a geometric construction over here. You have positive charge, you have a negative charge, and so definitely this line from here, and you have to let it draw a perpendicular over here, and if this angle is theta, then we can prove that this angle is also theta. I mean, we can prove that one is also theta. I mean, if you want, I mean, we can do it together. If you want, I can do it together with you. So this is D. Okay, this is R plus. This is R minus. If you subtract R plus minus R minus, that means the path difference. It's very similar to the Young's double slit experiment. If you remember, we have a path difference, and this is the path difference over here. The path difference is like if you have a D over here, then it will be D sine theta or cosine theta. You said cosine theta. Why I made a mistake over here? Okay, I changed the theta over here. We're gonna prove this one. This angle is theta. Okay, later on. So it will be this cosine theta. D cosine theta. Because you know this D, and this is the R plus and R. This is the delta L. R plus or R minus R plus. R minus R plus. Because this is longer than this one. Because this is, if you draw the perpendicular, anything after this perpendicular they are equal. This is the path difference. Okay. This is D cosine theta. Now, once you have this one, just put like in place of this one, D cosine theta. D cosine theta. So that will be D cosine theta divided by R square. This is R square. Now, you can go a little bit further. If you multiply Q and D, that will be the dipole moment, because dipole moment P equal to Q times D. Okay, and K P cosine theta divided by the dipole moment, and V net equal to, so V net gonna be K P cosine theta divided by. Okay, this is how I derive this one. But one thing I want to ask you, since we have given that this is the angle, the angle is theta. This angle is also theta because these two lines are parallel lines, and this angle is equal to this angle. This angle is equal to this angle because they are corresponding angles. Okay, they are corresponding angles. Okay. So and then this angle is theta. Then you use the cosine theta to get this value. All right. This is the net potential at a point P due to a dipole. the very important point over here that the potential depends on angle. The potential due to dipole depends on angle. If I ask you to find what is the potential A point here, point P, what will be the, assuming that this is going to make 90 angle, what will be the potential at point P? New point, let's say P prime. What is the potential value? What is the potential value at P prime? 0. Because it's a cosine 90. Cosine 90 makes it 0. And I can even prove like that. Because if I have this point is at the center, distance r plus gonna be same as r minus. If I put r plus is equal to r minus, this will cancel out. This is consistent, right? So this is very general expression for finding the potential due to a dipole. And we have a maximum potential when you got theta is 0. That means if I consider another point P double prime or along the axis of the dipole, that has a maximum potential. Okay, because it has a cosine 0 and cosine 0 has a maximum value of 1. Okay, if I am consider the perpendicular to the axis of dipole like this, it will be 0 because theta gonna be 90, cosine 90 is 0. Anyway, so this is about the potential due to a dipole, and there's one example. I believe this is the one example where you can use the same expression to find the potential due to dipole. And we are talking about the ammonia molecule, ammonia NH3. I think some of you guys already know. The ammonia, the nitrogen is in the ammonia is very electronegative. It pulls the electron from hydrogen and it creates a dipole. Okay? The chemistry, you might, you have taken the chemistry class or not. Ammonia is a polar molecule, so basically you have separation of charge because of the strong electronegativity of nitrogen. Okay? And the dipole moment is given, this Q P value is given, it is equal to 1.47 D. D is like, has a unit of conversion factor of 3.34. So let me do quickly over here. You have ammonia molecule and dipole moment is given 1.47 D. So D is like the same as 1.47. The conversion factor is that 3.34 times 10 power minus 30 coulomb meter. And from here you can easily see that it's 10 power minus 30, right? It's a very small dipole moment in ammonia, right? Ammonia molecule has a dipole moment, but it will be small, pretty small. Okay. We have given this one over here. So the question is that what is the electric potential due to ammonia molecule at a point 52 nanometer away from the axis of dipole? So you have given R value, that is also very small because you cannot have a dipole like in a meter, so it's a nanometer. So the value of this electric potential I need to find in 10 to the power minus 9 meter. So I need to find what is the V net over here. So you have given the P, you have given the R, and you know what is the K value. What about theta? calculate the electric dipole, electric potential due to ammonia molecule at a point 52 nanometer away along the axis of dipole. Along the axis of dipole means theta is 0. So you have everything, you can just use this equation to get a potential, okay? So I basically just leave as an exercise. It's a very simple problem, so you can easily figure out. So all right, so I can start a new topic after this, new chapter. But before that, I'm going to tell you about electric potential due to a point charge and equipotential surface. Okay. So you know that the potential depends on distance. Let's say you have a point charge, positive charge, and you are trying to find what is the potential at a distance of r. Okay. The potential is given by K Q divided by R. Let's say you have R1 distance, you have R1, D1.
Where's the other question?
That's what we are discussing for a long time.
Where-
If I consider another point at the same distance R1, the potential value gonna be also same, right? Because you have the same distance, you have the same charge. K is the Coulomb potential, it's a Coulomb constant. Whatever the potential you have, let's say 100 volt over here, you will have also 100 volt over here. Isn't it? It's just a function of distance. If you have the same distance R1, any point you consider over here, another point also, let's say R1 same distance, it also have a 100 volt. If you consider over here, it's also 100 volt. And you don't have to worry about the direction because it's a scalar quantity, right? What that means that any point, okay, you can draw a sphere or any surface like this. If the distance is same, and you have a point charge, you can have a sphere or you have a circle in 2 dimensions. Any point on this surface, if you consider any point, it will be the same distance, you have a 100 volt again. And if you consider this point, you have a 100 volt. Any point. As long as you have the same distance, right? It's a function of distance. So it makes like a circle in 2 dimensions. If you consider like 3 dimensions, you have a like a sphere. This kind of surface is called equipotential surface. A surface that has the same potential, equi means equal, or same potential. A surface that has the same potential is called equipotential surface. You can choose any point on the surface, it has the same potential, but the distance is same, okay? Over here, you have like a chart, for example, in the slide, and you can have like many equipotential surface. If you consider nearby at a distance of r, you have like this potential surface, and you have another like one. There are many equipotential surface around the chart, and remember that the potential depends on the distance. If you go very far away, the potential decrease, right? Because You have a larger R value means you are in the denominator, you have a large number, your potential decrease. So that is the reason that if you consider the equipotential surface a little bit further, you have a smaller value. For example, this one has a 400 volt, this is a 300 volt, this is a 200 volt. The most outer one is the 100 volt. It's decreased. Okay? If you keep on decreasing, keep on go further, if you go very large distance, like infinite distance, the potential will be 0. Okay? So it's like you are decreasing at some moment, it will be 0. So this is called equipotential surface. The general description of the definition of equipotential surface. A surface having same potential is called equipotential surface. Okay. So with that, I'm gonna finish this chapter and start a new chapter, and that is the chapter 25, and it talks about the capacitor. Most of you guys are from the engineering background, and if you have electronic engineering is a major, electronics is a major, then you have to deal with the capacitor, inductor, and resistance a lot. So let's talk about the capacitor, okay? And capacitor is an energy storing device. Okay, in the electronic circuit, we need capacitor. For example, it's a small section of it's a circuit board over here. I think you're gonna deal with circuit board a lot in the engineering. So a small section of either is a television or like a laptop and circuit board. And you can imagine that how many capacitor. The capacitor over here is like a cylindrical shape over here. You can see cylindrical shape over here. Even in small section of the circuit board, you have so many capacitors. So you can count like a number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you can have even more over here. So these are all capacitors. Okay. So it's a very important piece of like a device in the electronic circuit. Okay. And a capacitor is an energy storing device. It stores the energy as electric potential energy in the circuit, and whenever you need, it releases the energy. Okay, so basically, it stores the energy inside the circuit board, and once you need to release, it just releases the energy. Okay, it's like I don't know how many of you guys. You must be very familiar. If you go to hiking, nowadays, we just have a backup. So power bank. Right? So basically, you want to charge your cell phone, right? So you have like some backup, right? And nowadays it can charge even 2, 3 phones, or the same phone it can charge more than 5 times. Okay, what you do, you have like a capacitor over there. You store the charge over there. Okay, definitely there will be some circuit, like to release the charge to the whenever you charge the cell phone, right? So basically, you store the the energy in the power bank. Okay, so this is the incentive. Okay, basically a capacitor is the energy device, energy storing device, and it's a very important piece of information, piece of equipment, or like a part in the electronic circuit. And there are many kind of capacitor. Some of the picture I have shown over here. There are some of them is a cylindrical shape, and you have like some shape like this kind of shape also. There are many kind of capacitor. So the basic, fundamental principle of capacitor gonna be same. Okay, so it doesn't matter what kind of shape it is. There will always positive charge and negative charge. Okay. So we're gonna talk about one kind of capacitor. Is called parallel plate capacitor. And I told you that even if we exactly do not follow the capacitor we have, but the principle for the parallel plate capacitor and others will be the same. So let's talk about a special kind of capacitor. So parallel plate capacitor. You have 2 plates, and they are parallel to each other. So you have two plates over there, and they have placed parallel to each other. So simple design, you have two plates over here. So you have two plates like this. One is they are identical. They have same cross section area A. I mean, this is a like front view.
Finally got
Same positive charge.
plug it in.
So you have cross section area A, okay, and you have a separation between them is a D, okay. So parallel, I mean, plate means I have two metal plates. They are placed like this. The front view. If you want to see the side view, it looks like this. I mean, you have a two metal plate with positive charge,
Plus a quarter, like minus 4.
and you have cross section area. So you have a length, you have width,
Like that.
you have like cross section area. You have like a negative charge. One is positive charge and the other one is negative. They are identical plate, by the way. Whenever I draw equivalently identical. For drawing scale. And you have the same, I mean, cross section area, and you have the separation is D. The cross section area is A. And one is positively charged, another one is negatively charged, but the magnitude of the charge is going to be same. Okay? Let's say, for example, if you have a positive 2 microcoulomb over here, this one also have a 2 microcoulomb. They have the same charge, okay, 2 microcoulomb, but this is a negative charge, okay. The magnitude is going to be same. So this is the side view of a capacitor, and this is the front view. You have a charge Q over here. And so in between these two metal plates, you have a small separation. And either you have like a vacuum, there's nothing in between. But nowadays, they put like some dielectric material. Okay, so sometimes there will be nothing, and sometimes they put like some dielectric materials. Okay, some plastic or paraffin or something, or some glass.
Looks like that.
And we later on show you that we're gonna have the like information that if you place a dielectric material, it will increase the energy storing capacity. Okay, so nowadays like because every day we want to make an electronic device faster, efficient. Okay, and I mean people came up with the idea that hey, if you put some like a dielectric material in between plates, then it will increase the energy storing capacity. Okay, so that we'll talk about that. And a parallel plate capacitor made of two plates of the area A separated by a distance D. This is what I exactly told you. And so the charge on the facing plate have the same magnitude Q but opposite sign. I will explain to you. Okay. So this is general instruction, general information about the plate. And so definitely, if you have like a positive charge and negative charge, you have an electric field, you have electric potential. So potential B, let's say electric field. This is we consider positive charge and higher potential, and negative charge and lower potential. You have potential difference, delta V. Okay, delta V. And if you have a potential difference, and then D, you have an electric field. Okay, so let me talk about that. And the charge in the capacitor. In the beginning, whenever you have a two metal plate, you may not have like it's not charged, but you can design a simple circuit like this. You connect this one to the switch with the battery, then you can charge the capacitor. It's a general information. I will go to this one. And so there are a couple of things we have to talk about. We can use the Gauss law again. We can use the simple Gauss law again to find some of the important piece over here. So Gauss law we use already to calculate the electric field, and for the linear charge distribution, point charge, in the last couple of lectures before the test tube. And we can use the Gauss law again over here, and to find some of the quantities over here. So a couple of formulas over here. That the charge on the capacitor is given by, you can call the capital Q small q or capital Q is given by epsilon naught EA. If you use the Gauss law like that, do the integration, net charge is like a Q over epsilon naught, flux is given by E times dA. If you consider A is the area of the cross section, then you can use that equation to get the charge on the what is the charge value on the plate. So and there is a one very important point over here. The charge is directly proportional to delta V or delta V. The charge on each plate of the capacitor is directly proportional to the delta V. So in the physics, if you have proportional sign, if you want to remove this proportional sign, replace the equal sign, you have to put a constant. I just put a constant as C and delta V. The C is called capacitance. This is a constant. It's called capacitance.
You should get 3.
Each capacitor is characterized by a capacitance value. Okay, it's a constant value for a given capacitor, and if you have a capacitance is higher, then it has a more energy storing capacity. Capacitance is a constant. I just placed the constant. It is a constant value for a given capacitor, and larger the value of this capacitance, it has a more energy storing power. The energy stored by a capacitor is given by the formula. We can derive these formulas, but I just want to put like that. So 1/2 C delta V square. If you have a larger value of C, then you have a more energy storing power. See, U is the energy stored, potential energy stored, energy stored by a capacitor is given by 1/2 C delta V square. Delta V is the potential difference between the plates. Okay, so you have a more energy storing power if you have a capacitor with a larger value of capacitance. And there are many other equation that relates the other physical quantities over here. We could derive those things, but I will not go into detail over here. So over here, let me summarize this one. A parallel plate capacitor has 2 plates. One is positive charge, and the other one is negative charge, and they are separated by some distance d. And over here, Q is the charge on this plate. Let me write down this one because you might forget. Charge on this plate. The charge on each plate is plate. So we have the same charge value, but they are opposite in nature. A is the cross section area. A is the cross section area or area cross section area.
Like this, but in the negative half plus
okay? And D is the separation between them. D is the separation, okay? Separation. Yeah, separation between the plates, okay? And in between these two plates, you know, usually we have a vacuum, okay? You have a vacuum, there's nothing, or like you have air, but you have like nowadays, you know, you have some dielectric materials, and so since this is positive charge, this is negative charge, we take this is a higher potential, this is a lower potential. You have a potential difference, that's a delta V. Okay, delta V is the potential difference. Potential difference between the plate. Okay, the potential difference between the plate. And we have since this is the positive charge, the negative charge, the electric field line. The electric field line is like this. Electric field line, you know, like it starts from the negative, it's a positive charge, goes to the negative charge. I think you know about this one, okay? And if the electric field lines along like a straight line, the electric field also gonna be tangent gonna be like that. So this is the general information about the capacitor. So there are many formulas, you know, I'm gonna discuss about later on. This is one of the example of parallel plate capacitor. The parallel plate capacitor. Parallel plate capacitor. So there are other kind of capacitor. You might also notice that, you know, cylindrical capacitor. In the cylindrical capacitor, you definitely have a positive charge and negative charge. They are separated by some distance, but you can see that you have the structure is like that. You have a like inner cylinder over here, your outer cylinder over here, your cylinder over here, and it's like vertical view, okay? And you have positive charge and you have a negative charge. The same principle that you have positive charge, you have negative charge. They are putting like parallel in the parallel plate capacitor. But in the cylindrical capacitor, you have like a cylindrical shape, right? The inner cylinder is positive charge, outer cylinder is negative charge. You have always positive and negative charge, and definitely you have some separation between them. Because if you put like two charge together, then basically they neutralize, right? Positive charge, negative charge, they combine together. So you want to have some separation between them. That's the exact reason that you want to have like some separation over here. Okay. So so this is the cylindrical capacitor. The design is like that, and depending on what kind of like capacitor, the formula to calculate the capacitance and the charge gonna be a little bit different. Okay, that's gonna be a little bit different. So in the cylindrical capacitor, so I mean, you already saw in the figure over there, and I even discussed about that. You have a positive charge over here. I mean, it's like a vertical view, okay? And then you have some separation. You have, like a, I mean, outer cylinder is, negative charge. And my figure will show that. So put like that, it says positive charge. And let's say you have enter. Better picture, please, take a look on the slide. It's a negative charge over here. It have, definitely, you have a separation between these two, this metal. this is also metal, okay? But this is the shape is like a like that, cylindrical shape. You have an inner cylinder and outer cylinder, okay? The charge, I wrote the charge is epsilon EA for this one. You have the same thing, but like for cylindrical capacitor, the Q value I just write in capital Q, okay, is given by epsilon naught E. A area is like given by, because it's a cylindrical shape. The shape is given by cylinder. So this is equal to 2 pi RL. Okay. Basically this is the shape gonna look like this. Let me show you the like in a side view. Side view like this. There are two cylinders coming over here. Outer and the inner. And the L is the length. And all of these inner cylinders for that. And if I want to find the capacitance value, this formula is given by C is given by 2 pi epsilon naught L over logarithm of B over A. B and A, they are the radius of the inner and outer cylinder. Okay, inner and outer cylinder. Okay. So V is the, if you consider center, you have a consider center, and you have like a B is the inner cylinder and outer cylinder is A. And R is the B is the outer side. Inner is like this is inner. Okay, this is about the cylindrical capacitor, and similarly there will be some other capacitor. We are not going into detail, but we want to give some information that so spherical capacitor, you have like a sphere shape spherical capacitor. That kind of capacitor also exists. An isolated sphere capacitor, you also can have a one single charge that also acts as a capacitor. It's a special condition that if you have like one metal piece, like a small metal piece, even if you don't have a negative charge around it, it acts as a capacitor. Okay, so this is a special case. We are not going into detail in our class. We only focus on this parallel plate because this is the easiest one. Okay, it's the easiest one. Even if we do not go through the other capacitor, the principle of how a capacitor works is same. Okay, so how a capacitor store energy and some unknown physical quantities, the behavior gonna be same. So in this class, we just talk about the parallel plate capacitor over here. Okay, so but in your class or in your in a higher level electronics class, you might see some other special kind of capacitor like cylindrical capacitor, spherical capacitor, or isolated plate capacitor. Okay, so just keep that in mind. Okay, let's talk about some of the important formula that for the parallel plate capacitor. So parallel plate capacitor, as I mentioned, you have some important formulas. I just read over here. I already wrote some of them already, but let me revise this one. The charge on a each plate, number one, is given by Q equal to epsilon naught EA. Okay, where E is the permittivity of free space. Okay, and it has a value of 8.85 10 to the power minus 12. And E is the electric field. I'll just write down over here. E is the electric field. Electric field. Okay. And over here, A is the cross section area. Number 2, Q is C times V. Some people say delta V. Okay, V is the potential, but delta V. You can have like the same, same way. And number 3, the capacity is given by F naught E over T. This is like some important piece of formula. Again, the energy stored is given by U is given by 1 over 2 C delta V square. So these are like some important piece of formula. And you don't have to even memorize this one, but you need to know what to represent what, okay? This is charge, this is the capacitance, and U is the energy stored by the capacitor. Okay? So with that, let's do 1 or 2 problems, and then we're going to keep on talking about this one in the next lecture as well. We have 10 minutes, and I might have a couple of problems over here that we're gonna think of. So there's 2 problems. I'm gonna solve one of them, and I'm gonna assign one as a homework for you. Okay. So let's take a look on this problem. Alright, so I don't have any preference to solve with the 1 and 2 is the same thing. Okay. I just want to start 1. I mean, if you want me to solve number 2, that's also fine. So basically, your parallel plate capacitor has a circular plate of radius 8.2 centimeter, radius and 1.3 millimeter separation. You have a parallel plate capacitor, but this is made out of circular plate. And the radius of plate is given. The plate has a circular shape. You have a parallel plate, but this plate is not rectangular like this. I mean, I have to draw a rectangular over here, right? The shape is rectangular over here, right? But according to this question, you have a parallel plate, but this plate is circular. Okay? So whenever you draw like this. I mean, it's a circle, I mean, for me, okay? I mean, I just want to draw 2 circles. And they are placed parallel to each other because it's a parallel plate capacitor. Okay? D. And try to make sure that both are, almost same shape. I hope that it's the same shape. Definitely, according to that parallel plate capacitor, one is positively charged, another one is negatively charged. Yeah, just like that. And charge on this one, positive Q, positive Q, and this is negative Q over here. And you have separation of distance D. And we have given the radius because this is a circular plate. And the radius is given. I mean, you can make radius like this. R is the radius, Now circular plate is R is the radius, okay. R value is given, which is equal to 8.2 centimeter. You can change this one to meter, definitely 8.2 times 10 power minus millimeter. Okay. A parallel plate capacitor that is made from the two circular plate, and we have given the radius, and we have a separation of 1.3 millimeter. This is D value is given. The D value is given in millimeter, 1.30 millimeter, and definitely you want to change this one to meter, 10 power minus 3 meter. These are the given information. Now, you need to calculate, I mean, identical pattern making a little bit better. I need to find capacitance value. In A, we need to find C value. So I just come over here. No, we don't have that many formulas over here, right? For the capacitance, we have only 4 formulas over here. 1, 2, 3, 4. So number 1 is about charge. I don't have that. I have to calculate the C. Number 3 gives us capacitance value, right? So this is given by. So we can use the same formula. In the A, C is given by epsilon naught E over T, and epsilon naught is the permittivity of free space, which is a constant number. If you don't remember, I definitely provide you in the exam. 8 point. What is the value? What is the value? The permittivity of free space. Is 8.6? 8.86?
Yeah.
Negative? 12. I mean, we don't have to memorize this one definitely, right? So, I'll give you the example. A is the cross-section area. Remember that this is a circular plate of radius r, right? If you have a circle of radius r, what gonna be the area of cross section? Pi r squared. Area gonna be pi r squared. So you have given the radius. So you have a pi. R value is 8.2 times 10 power minus 2 square divided by D is given. Whatever the value is 1.3 times 10 power minus 3. So whatever the value you came, that's gonna be your capacitance, and capacitance is always measured in the unit of farad. M. Okay, the unit for the capacitor is farad, so I just put like a F. It's a symbol.
Got it. I got 1.43. Can't see your case. I'll just compare what I did.
What did you say that unit was?
I'm sorry?
What did you say that unit was?
Oh, unit is farad.
Oh.
Let me. This is a very important piece. You know, you might see in that
That's exactly what I did.
the true and false question. The capacitance is measured in the unit of capacitance,
Calculator's is better. It's for real.
and the unit is and we will just say N as a
That's exactly.
unit for the capacitance. Okay, number A, I don't know, I don't have a calculator, you have a calculator. please you can calculate that one, and you might get the answer for that.
Let's get these
In a B, because of the time I need to rush faster. Over here, find the charge for a potential difference of 120 volt. You need to find the charge on this one. You need to find the Q value, and given that potential difference is given, the delta V is given over here. If delta V is equal to 120 volt, then what is the Q value? So I just erase the formula over here. I just erase the formula because I wrote this unit over here. So there was a formula that gives the Q value. Q is given by, I think I see there, Q is given by C times delta V. Delta V. And from the part A, you already got C value. Just plug in whatever the value. And delta V is just given 120 volt. Given this one, you have a charge, and the SI unit for the charge is coulomb, and this is C. Right? It's a charge on the system. Any questions so far? Alright, so if you do the calculation correctly, I believe you're going to get the same answer. Let me know if you're going to get the same answer. With that, I want to finish the class for today. So next time, we're going to talk about the, more about the